capacitor behave differently, but they're all basically related. They're all sinusoidal, but they're like cosine either plus 90 degrees or minus 90 degrees or just directly. You can do that in terms of imaginary numbers by introducing something called the reactance. So you define what's called impedance actually. So you define something called impedance. It's a complex quantity, and it treats resistance in the real direction, inductance, and capacitance in the imaginary directions. And essentially what it means is that you can treat RLC circuits with sinusoidal sources as if they're DC circuits. So they really should teach that to you, the electrical engineering here. Maybe it's in a later class or something. But you're currently in circuits?
Yeah, just DC circuits.
Why on earth is this not a prerequisite for that class?
I don't know. It's interesting.
Anyway.
Differential equations isn't a prerequisite for circuits and linear.
Yeah, so I don't know. Look, I think I told you guys in class, we had to teach, this stuff up here in Calculus 2 when I taught Calculus 2 at NC State, because exactly the issue that you're with right now in the basic circuits course, you study these very simple circuits, and you need this very simple mathematics to solve it. This is so much easier than like trig substitution or I mean, heavens, like convergence divergence is 100 times harder than this, easily, logically. It's so much harder. Yet a dozen theorems and 30 different logical paths to go down, This is solve a quadratic equation. There's 3 cases, done. I digress. Look, this problem again. I don't think I even changed it. Out of page, right? I'm just super lazy. Now, I don't post the solutions, so unless students happen to pass them from year to year, which, see, we don't have fraternities, so I'm more or less safe. And the internet wasn't as much of a thing when I did this. So the cheat sites were not nearly as organized as they are now. I don't know, maybe people had them. Maybe I didn't give them a formula sheet this time either, I don't know. Maybe. This is an LC circuit. So again, I think I must have spent like a whole day on differential equations in this particular semester. So anyway, but this one I do want you guys to know, Q prime prime over LC, that has the solution, and you're given the initial charge in the initial current 0, so you can solve, and you get that Q as a function of T is this, but then dQ dt is the current, which gives you that. And so the maximum current is when the sign is 1, right? Or minus 1, I guess, in this case. So Q naught over square root of LC, which works out to that. That's my maximum current. And how much time does it take for that current to be reached? Well, you got to think through things there, don't you? So so since this is minus sign, the graph of the current looks like this, right? So to get to the maximum current, I need to go 3/4 of a cycle right there. So, yeah. Or what did I say here? Maximum current. Did I say quarter period? Oh, magnitude, then it's the quarter, right? That's the maximum magnitude that happens after a quarter period. The actual maximum appears at 3/4. So I need to read my own problem magnitude. Anyway. What's the energy? Q squared over 2c. And so I do think part C is a good question. That's a good question. What's the energy stored in the LC circuit? It's Q squared over 2c plus 1/2 Li squared. And C, like I did in class for you guys, I showed that, sine squared plus cosine squared is a constant. So we have that total energy being shared back and forth between the inductor and the capacitor in this situation. What's this? This again? Come on, so boring. Same question again and again. I guess I got stung by the 2013, the hollow one. I was like, I don't want to do that again. I want to make it solid, see if that helps.
Just make it a hollow square.
Make it a hollow square. So here's a triangular loop, distance r, and we pull it away. Oh, is that what anybody? Yeah, I did this with. Or did we let it go into? No, we had a triangular loop that we put into a uniform. We had a triangular loop that we moved into a uniform magnetic field region. Oh, we did this one also? Okay. Man, I can't remember what I've done this semester. It's not a good sign. Oh, I did this right after the easier one.
Then you joked about making the angle variable. I'm not like that, so I'm
Make the angle variable.
the angle that goes in, like as it moves into the field.
What if this turns? What if it like spins? Then what happens?
I assume if it spins like that, it disappears. It's flat, so.
Oh my goodness. Optics, yeah. I don't, you guys do that in lab. I leave that for lab. I'm not sure what this is. This must be the details of the, what is this about? I don't know what this is about. Oh, that must be the derivation of this thing. Oh, OC over, right. All right, so well, like you said, we worked that out in class. Oh, there's more? Oh. All right, there's more. So you've got a current one, oh, two currents. Ooh, fancy. I've got a current one of 300 amps, yowzers, flows into the page at 1.3, and current 2 of 50 amps flows out of the page at minus 2.1. Find the magnetic field at the origin in terms of the magnitude standard angle. So we got to figure out, you know, for current one, like that, right? And it should be perpendicular, the B1 should be perpendicular to that line, right? And B2 likewise should be perpendicular to that radial line from the origin. Yeah. And then it's just a matter of trigonometry and such to try to figure out, you know, I think I've used, is that the same theta? Okay, so yeah, okay, so I'm two different, these are two different thought bubbles. This is just for figuring out the magnetic field from the first current. So I'm relating the angle here to the angle there, which is apparently, you know, inverse tangent of 1/3. And so I need, you know, that's also that. So B1, it's got a negative x component, but a positive y component, whereas B2, on the other hand, is going to have a positive x and y component, right? And so I just work out the geometry of the problem down here. So like this problem, hey, we're right back to first semester, like first test, add vectors, break down into components, find the standard angle, find the magnitude, all that stuff. So yeah, this is not a hard problem, but it does require attention to detail, and you got to believe you can do it too, right? You can't just throw up your hands in despair. You got to believe you can make it through, because you can. It's actually not that hard of a problem. It just, you know, you got to one thing at a time and put it all together. Oh, another. All right, so this is this I can't test yet, I think, because I haven't talked enough about the formula for the electromagnetic field, so I'm not quite at peace with this question yet. I think technically this is sort of on the bubble of what might be reasonable to ask you guys, in that I give you the formula for the electric field, and then I ask you questions about like what is the magnetic field and what's the Poynting vector. It's a little bit unfriendly because you have to kind of, no, it's not a fair question for you guys. I stick by my guns. See, because you have to look at the formula and go, oh, okay, so this means that it's traveling in the y direction and it's waving in the yz plane, the electric field is, which means that the magnetic field is going to be waving in the xy plane. And then I got to sort through the things to figure out that the direction, that the magnetic field is given by the same formula, but with an x hat rather than a z hat. Let's see here. But anyway, like I said, I might put that on the final if we talk about electromagnetic fields again after test 3. But otherwise, it wouldn't be a fair question. Because I don't think that was in your homework, was it? I don't think so. Oh, and here, yet again, this kind of question, right? We haven't done Snell's law, so what a great scuba man. That's I probably spent 30 minutes making that scuba man. Or what else we got here? All right. Wonder what this is. Wait, do you guys have any particular questions about anything? Oh, all right, I think we'll stop there then. So. Oh, man, I am worn out. Stupid transformers.